So we're going to start talking about resolution and numerical issues. Who's done a course in numerical methods before? All right. So who's seen finite differences before? Who's seen Taylor series expansions before? Who loves Taylor series expansions? You and Zeb were the only people who kept their hands up, right? Love Taylor series. Okay. So what I'm going to talk about today is parametrization, effective resolution, and then something called implicit numerical diffusion and dispersion. Just because that's something that people often talk about, but I've worked out over the years that many people don't know exactly where it comes from. This is still working, yes. Let me just fix my... That's better. Okay, parametrization. Heard this term before. Spelled differently depending on where you are, and you'll see everyone use these spellings interchangeably, and it's really annoying. So parametrization with an S and an E is the Australian spelling. You'll hardly ever see that, right? Parametrization with a Z and an E is the US spelling. So parametrization, quite simply, is representation of unresolved processes in your model. And we formulate parameterizations as a basis. They work off what the resolved scale flow is doing, what your model is resolving, and some approximation that links the resolved scale flow to unresolved processes via theoretical or empirical relationships, or machine learning relationships as well. So really what a parameterization is trying to do is say, if this is the large scale flow, what is the small scale flow? But what it really is doing is, for a specific resolved scale flow, what is the unresolved flow, and how does this then feed back on the resolved flow? And I'll go through the messy algebra of this to show you why the unresolved flow actually does feed back on the resolved flow. Now, there's no unique way to tackle this. I think it's safe to say that the parameterizations are arguably the weakest part of our models. Many of them are poorly constrained by observations, or difficult to constrain by observations, because they're quite small scale transient processes that are hard to observe. There's no unique way to tackle this. The approaches are normally deterministic, which means that if you have a certain resolved scale flow, your parameterization will give you one answer, and then if the next day you have that same resolved scale flow, that parameterization will give you exactly the same answer. So that's what deterministic means. But really these should likely be stochastic, because very small differences in large scale flow can lead to large differences in the small scale flow based on chaos theory. Some of them can be diagnostic, some of them can be prognostic, and I'll show you what that means a little bit later. Okay, so what needs to be parameterized in our models? Yell out some things, some processes. Turbulence, precipitation. What was that? Radiation. Excellent. What? Clouds. Boundary layers. Aerosols. What else? Pretty much everything. All right, pretty much everything. So deep convection, shallow convection, microphysics and clouds, turbulence and mixing, chemistry, gravity wave drag. No one said that. Should have said that. Gravity wave drag is when atmospheric waves propagate up into the stratosphere and mesosphere and break, and they exert a huge tendency acceleration on the mean flow, and which is not resolved. Because most of our focus is on the troposphere, none of us really think about gravity wave drag very much. Aerosols, chemistry, surface drag, surface friction, boundary layers, all these things. And I'm certain I've missed some things here. Now, some of these, the philosophy behind some of these parameterizations are quite different. I'll talk about that in a few minutes. And I haven't included land surface here because I see the land surface processes as a separate model that is coupled to our atmospheric model. But others may, well, the people who write atmospheric models view that slightly differently and often just have a land surface parameterization. So, I'm going to scare you with some equations that aren't that scary. There's just lots of them. With a finite grid spacing, represent our model on a grid. Part of our solution will be unresolved. Think about this room as one grid box. There's lots of variability inside this room. Think of each of you being a turbulent eddy. Right, so here's our grid box, and we have 68, 69, 70, 71 turbulent eddies in this room that all have their own characteristics and variability. And there's regions with lots of eddies and there's regions with no eddies. Right? So that's the parameterization problem. Trying to average out the effect of all the variability in this room on what's going on outside this room. Okay, so that's parameterization. So part of the physical solution will be unresolved. And I'll talk about effective resolution a little bit more detail later, but if we had 10-kilometre grid spacing, which is basically our high-resolution numerical, now our regional numerical weather prediction or our super high-resolution climate model, 10-kilometre grid spacing, signals with a spatial scale of about 100 kilometres or more will be well resolved. Signals with a spatial scale less than 20 kilometres, so 2 grid spaces, will be unresolved. And signals between about 20 and 100 kilometres spatial scale will be partially resolved. So let's ignore the partially resolved stuff for the time being because that creates major headaches with parameterization. Let's just separate our signal and let's do it with our velocity signal, u, into a resolved part and an unresolved part. So here's our velocity u and w. We're just going to do this in 2 dimensions. Our resolved part, u with a tilde over it, and our unresolved part, u with a perturbation. Now this is called Reynolds averaging, and some of you have seen this before. I'm just going to go through it. I'll go through it quickly. I'm not going to go through every algebraic step. So the key thing is that we're saying that u tilde is the resolved part of the signal, and the average of u tilde over the grid is equal to u tilde. So u tilde is considered to be constant over the grid cell. And the unresolved part of the signal, u prime, the average of that over the grid cell is 0. Right? So that's the assumptions that we're making. But if you multiply the resolved part by the perturbation part, by the unresolved part, take the average, it equals the mean times the average of the perturbations, which is 0. So there's only a few products that when you average them together give you non-zero signals. All right. I'm not going to go through every one of these. Now, this is a slide that I used in a class a couple of years ago, and one of the students in the class found a mistake on this. I haven't been able to find that mistake again because I forgot to note what it down is. So if anyone finds the mistake, Melissa's going to give you a prize. Okay, so we've got our equations of motion, just the zonal momentum equation, non-rotating, so it's just the advection of velocity with our pressure gradient. And we can rewrite this assuming a non-divergent flow. So that's an incompressible flow. So this is just a simplification. And you can rewrite it in this way. These two things are exactly the same if the flow is non-divergent like this. So I'm going to suggest that you go back in your own time and prove to yourself that this equals that. We're not going to do it now. Now, if we separate everything into a resolved part and an unresolved part, resolved part and unresolved part for zonal velocity, vertical velocity, and pressure, and substitute all of those into this equation, we get this relationship. We haven't done anything smart here, we've just substituted this into that equation. And then we multiply that out, multiply each of these terms out, and you get this super long equation. Now, this super long equation is exactly the same as this short equation. Right? And the thing about this, by doing it this way, you end up with these terms where there's a resolved term on its own, perturbation term on its own, products of resolved terms, products of resolved imperturbations, and products of perturbations. So there's lots of these nonlinear and linear terms in here. Now let's then average this over the grid. This is the Reynolds averaging step. Average all of these terms over the grid. Still have all these terms in here, which we had before. I haven't done anything from this step to this step except just put little brackets around it.
I think 1 by 2 you will say in the equation when you write rho by rho AU, current plus U was, not 1 by 2 should be there.
Which one?
Where you write recall U equal to the next line. So and second term, from the left second term. Yeah, there should be 1 by 2, I think.
You think there should be a 2 there?
No.
No.
Because if you differentiate, U do U by do L. So if you differentiate, it will come.
This one? This one?
Yeah. So this will be 1 by 2.
No, that's 2. That's still right, I think. That's right. That's not the mistake, I think. All right, so we're going to take this big equation and we're averaging it. I've just rewritten that equation again. And if you go through that step of saying, okay, the average of the perturbations is 0, and the average of the resolved flow is the resolved flow. So the average of the resolved flow is the resolved flow. So average that, you get that. Average the perturbation, or average the unresolved flow, that's 0, so that term disappears. That term averaged just becomes that. That term averaged goes to 0. That term averaged doesn't go to 0. That term averaged sticks around, so we've kept that term. We've kept that term. That term average goes to 0. That term average goes to 0. That term average stays. You get that. That term average goes to 0. That term stays. All right, so now we've simplified our equation set. Let's assume that the resolved flow is incompressible again, and we get this equation. So all those steps, we get this equation here. And what you see is just our advection of the resolved flow equals the pressure gradient plus these 2 additional terms from the unresolved flow. And that's the Reynolds averaging terms, or the Reynolds stress terms, they're called. And what you can see is now we have this additional forcing on the right-hand side where the resolved flow is forced by the unresolved flow.
How would you average this equation? Why?
Why do you average?
Yeah.
Because it's a good question. So we're averaging over each grid cell. We're saying, okay, what's the average effect of those unresolved terms on the grid cell and on the tendency of the resolved flow? Okay. So by doing it this way, what we see is that the small scale flow, the average of the small scale flow, and it's the nonlinear interaction between the small scale flow, can interact with the large scale flow. And this is really the fundamental premise of most parametrizations, is that there's unresolved processes in there that would have had an effect on the large scale flow. So the key thing behind parametrization is to parameterize these terms. That's it. Sort of. So to be physically consistent, right? So this part of the parameterization problem is really just about physical consistency. To be physically consistent, our model must incorporate some forcing from the small subgrid scale processes, and we parameterize them. Now, this Reynolds averaging approach is the basis of parameterization of all dynamical processes. So just use the word dynamical there. Turbulence and mixing, boundary layers, surface drag, gravity wave drag, deep convection, shallow convection, all of these things are dynamical processes that if you made your model higher and higher resolution, you would eventually resolve them. But we have finite resolution, so they're unresolved, and so we need to parameterize them. And the terms that we parameterize are really these Reynolds stress terms. And there's similar terms for temperature, things like that. But the other processes that we parameterize don't come from the Reynolds stress terms. Think about physical chemical processes, microphysics, radiation, chemistry, aerosols. If we take our dynamical model and we make it higher and higher and higher resolution, we're not going to magically have these processes appear. These are external processes forcing the dynamics. And if you're being philosophical around this, you could treat all of these as separate models. There's a radiation model that is coupled to the dynamics. There's a microphysical model that's coupled to the dynamics. There's an aerosol model and a chemistry model that are coupled to the dynamics. They're separable. You could take them out, put them in, take them out, and they're interacting in a different way. They're interacting purely on the grid scale, which is quite different to the Reynolds averaging approach, where it's really processes that would be resolved if you increase the resolution. So there's a subtle difference there that's actually quite important. And here's some examples from radiation and microphysics as well. I'll give you an example on how a dynamical parameterization works. And I'll use turbulence because it's the most interesting for me, not for anyone else. So how do we parameterize these terms? These are the terms, the two Reynolds stress terms for turbulence that we need to parameterize. There's something called K-theory. And K-theory really tells us that we can parameterize or approximate these terms in this way. Relate the turbulent stresses or the turbulent mixing to some property of the mean flow. This K. All boundary layer parameterizations use this approximation. All turbulence, most turbulence parameterizations use this approximation. And so now we see that there's a way to relate the subgrid terms to the resolved scale flow. So we can change our Reynolds averaging equation, which had these subgrid terms on the right-hand side, replace those subgrid terms with resolved terms. And so now we have a closed system again. We don't have these annoying subgrid terms, unresolved terms. We now have an equation which is purely based on those resolved terms. So we've kind of solved the parameterization problem. And if K was a constant, this would reduce to what's called the advection diffusion equation, with K the subgrid scale diffusion coefficient. Now, this system isn't closed yet, it's almost closed. The closure comes from how to define K. And K is related, defining K would give us the closure. And you often hear that term, turbulence closure or parameterization closure. Closes the system of equations. So for turbulence, K is kind of simple to understand. K is really small when there's no turbulence. K is really large when there is turbulence. And the only way we can define K is by some property of the resolved scale flow, because that's all we know. We don't actually know the subgrid scale unresolved flow. So there's lots and lots of different ways to do this. This is the simplest way, which is called the Smagorinsky closure, which is in lots of our models. Most of our models have this Smagorinsky closure. It's based on this thing called the Richardson number. Who's heard of the Richardson number before? Good. Richardson number tells us if the flow is dynamically stable or unstable. 1 for Sala frequency divided by the square of the shear. If the Richardson number is large, the flow is stable. K is 0. We assume there's no turbulence. Once the Richardson number is small, we use this equation to define K. That's our closure. This is the simplest closure. This is the Smagorinsky closure. So now we can solve this equation, and every step you diagnose what the Richardson number is in the flow, you define a spatially varying K, and then you can step forward in time. So that is called a first order closure, where we parameterize the flux of the diffusion processes, and the diffusion coefficient, the K, is determined by a diagnostic relation. That's a first order closure. A zero order closure is you assume all your turbulence terms are 0 and really no parameterization at all. Right? So that's doing nothing, doing 0. But you can actually have higher order closures. The second order closure is actually you work hard and derive a prognostic equation for those unresolved terms. And if you do that, you'd end up with a triple product term like this, which is really ugly, and then you have to parameterize that triple product term. By doing that, you get a much more sophisticated closure, keeps on going, higher and higher order terms, more equations, more computational expense. So you have to balance this idea between complexity and computational expense. I think these kind of higher order closures are really nice theoretically. We really don't have the observations in the free troposphere to constrain them at all. So it's almost, there's very little point in going to these really complex closures that we can't evaluate very well. We can evaluate them in the boundary layer. We've got lots of observations in the boundary layer, but not in the free troposphere. Convective parameterization. There's one person in the centre who would get really cross with me if I didn't say that word. And he's speaking later in the week. So convective parameterization is a different approach, but it's a similar approach. It's based on these Reynolds stress terms. So parameterizing convection is defining these Reynolds stress terms in terms of some kind of mass flux, where you're parameterizing, your closure is really about parameterizing the flux of mass in convective clouds and using those to define the Reynolds stress terms. And the common approach, this is a really nice paper. If you really want to go back and read a classic paper on parameterization, this paper by Arakawa and Schubert in '74 is really nice. Really the foundation of all of our cumulus parameterization. Parameterizing within a grid box, there's a population of clouds. And that population of clouds is normally represented by a series of idealized plumes. And in each idealized plume, there's a derived mass flux, and the sum of those plumes defines the area of convective clouds in that box. So that's what's parameterized in convective clouds. Now, parameterization. The assumptions that are made for each parameterization is a separation of scale. And here's an example. One of our former PhD students from the Centre for UNSW, Maxime Collin, took this photo out of the window of his plane, and he was working on convection, so I thought this was pretty cool to take photos of convection. You can see, say this is our grid box. This is actually quite a small grid box. And we're trying to parameterize convection. And we've got lots of little convective plumes in there. But you can see that there's bigger clouds to the right of this, basically the size of our grid box. So this would violate one of our parameterization assumptions. So this assumption of a separation in scale between the resolved flow and the process being parameterized. So basically what it tells us is, this assumption says, you know, our grid boxes are much larger than what we're trying to parameterize. We've got lots of elements inside our grid box that we can average out. So this room is actually a pretty good parameterization example. If each of you is one of the eddies we're trying to parameterize, we've got about 100 of you in the room, and so there's this separation of scale. So for dynamical parameterizations, this is equivalent to saying that there are many individual elements that form part of that Reynolds average. There's not just one element that's part of that Reynolds average. There's lots of individual elements. For convective parameterization, it's the constraint is really the area of the convective plumes summed together is much smaller than the grid box. And this is consistent with the formulation of our parameterizations, which are really formulated as separate atmospheric columns with very little interaction between adjacent columns. Because there's so much stuff going on in the box, it doesn't really matter what's going on outside the box. And we don't have one element propagating from one box to the other. Right? So these are our assumptions. That worked perfectly well 20 years ago for our climate models when they had 10-degree latitude, longitude boxes. That assumption doesn't work so well anymore. It certainly doesn't work for our numerical weather prediction models either. So there's this term that you might have heard before called the grey zone. Who's heard the term grey zone? A couple of you, not many of you. Okay, that's fine. And this is a term that's become popular in the last 10 years. A while ago, 15 years ago, there was this really nice paper by Wingard. There's a few papers in the research literature around that time. It took a little bit of time for the operational meteorological community to catch up to this. Wingard called it the terra incognita. What's that? Who can speak Latin? What has happened to education these days that no one can speak Latin? It's like no person's land, to put it. Unknown land in here, right? So you think about the resolution, as resolutions increase, the parameterization assumptions are violated. So as the scales where the parameterized process become partially resolved, we have this problem, right? We don't know what to do. We're partially resolving our processes. Do we stop parameterizing them or do we keep parameterizing them? If we stop parameterizing them, we can get into trouble because we've got all these partially resolved signals that we're not parameterizing anymore, and we can get some really strange results. If we continue to parameterize them, we're using a parameterization that was designed to do something different. We're violating the assumptions that were used to derive that parameterization. So what do we do? And this is the fundamental problem in this grey zone, where we're partially resolving the thing that we're trying to parameterize. So think of large convective clouds. A large convective cloud has a spatial scale about 1 to 10 kilometres. Boundary layer eddies and turbulence have a spatial scale of about 1 kilometre or less. So if we have our Let's see our 20 kilometre resolution model. It's okay. No, our grid box is still much larger than convective clouds we're trying to parameterize. It's still much, much larger than the turbulent eddies that we're trying to parameterize. Bring it down to 10 kilometres, you start to have problems. At 10 kilometre grid spacing, we're now partially resolving those clouds that we're trying to parameterize. Turn that parameterization off, strange things happen. So normally models at 10 kilometre resolution still have a parameterization on, being used for convection, but all the assumptions behind that parameterization are violated. Once we get down to 1 kilometre grid spacing, we have a further problem. We're starting to resolve the convection properly, so we can switch off the convective parameterization and treat that explicitly. But our eddies in the boundary layer are 1 kilometre, 500 metre, 200 metre scale. So at 1 kilometre grid spacing, we're partially resolving those eddies in the boundary layer. So we're in a new problem area. What do? Do we parameterize the eddies or do we not parameterize the eddies? Do we parameterize the boundary layer or not? And so this region between about 10 kilometres and about 500 metre grid spacing is known as the grey zone, because we have a number of these processes that we're trying to parameterize, but we're in this intermediate zone where if we don't parameterize them, we get weird results in our model. If we do parameterize them, we're doing it with a model that we're violating the assumptions behind that model. There's a lot of effort going on right now to develop what are called grey zone parameterizations, so scale-aware parameterizations that are supposed to operate in that grey zone. I think this is a perfect time for me to pause and for us to have a cup of coffee and a snack, and then come back and we can continue. This is so we've got about half an hour to go. Wanted to speak about effective model resolution. And this is kind of the theme for the rest of this lecture, is on effective model resolution. I was at a conference a couple of weeks ago, and it was actually a workshop, and someone kept on talking about that they had a 1 kilometre resolution model, and one of the people in the audience kept on yelling out, "It's not 1 kilometre resolution, it's 1 kilometre grid spacing," right? And there's some people who get really upset about this, and some people who don't care. But the key thing is that if you have a model, and it's a finite difference model on a regular grid with a certain grid spacing, let's say 1 kilometre, just for ease of the argument here, you're not resolving anything properly on that 1 kilometre scale. And you're not resolving, the minimum resolvable scale that you can represent is 2 kilometres, so it's like some noise, really. You're not really resolving that properly either. You're not resolving anything with 3 kilometre scale properly either. And it's not until you get to much larger scale that you're properly resolving features. Now, we've known about this for a long time. Anyone who's done courses on numerical methods, you go through and you do the analysis of this, and you can show that all of your errors in your numerical schemes, the errors are maximised at the smallest resolvable scales. Right? So you start to get artefacts and errors that come in based on your truncation error, and that's maximised at the smallest scale. Here's a nice paper by Skamrock 2004, which looks at the resolution, or the changes in resolution of the Whorf model, and what is actually resolved and what is not resolved. And the key points are what I just said. Numerical errors are maximised at the grid scale. Models do not properly resolve the dynamics physics they're trying to represent on that grid scale. They're resolving them properly on larger scale. So here's the example. Different grid spacing of the Whorf model, 22 kilometre grid spacing, 10 kilometre grid spacing, and 4 kilometre grid spacing. And what's shown here is a spectral representation of the energy. Who's seen power spectrum before? Okay, most of you. So what we have here is wavelength along the x-axis. And wavelength is actually getting smaller because this is actually plotted as wave number, inverse wave number. But here, 10 kilometres, 100 kilometres, 1,000 kilometres. And the dashed line in each case is the energy density spectrum calculated from these Whorf model forecasts and averaged to create this one line. What's also plotted here is a line that it's a theoretical line, but it's based on lots and lots of observations from commercial aircraft to work out what the energy density spectrum of the atmosphere is. It turns out it follows this really nice power law relationship in the mesoscale range of about k, which is the wave number, to the -5 thirds. So this is truth. It's close to truth as we can get with our models. And at the mesoscale range, so this intermediate atmospheric range, we want our models to represent that. 22 kilometres, we're not really resolving the mesoscales properly, and you get this roll-off in the energy as you go to smaller and smaller scales, and it rolls off quite dramatically here. Once we go to our 10-kilometre grid spacing forecast, this mesoscale range, so from about 50 kilometres or 60 or 70 kilometres and longer, the model matches the observations very well, or the theoretical observations very well. And same when you go to 4-kilometre grid spacing as well. There's a slight difference in energy density, but the slope is right. Where it deviates is here, these smaller scales. And that deviation occurs at about 7 times the grid spacing. And you see a rapid reduction in energy density at these smaller scales. So the model is resolving the longer scales very well, but as we go to smaller scales, the energy is damped. And that's really what defines the effective resolution of our model, the start of that damping. So for 4 kilometres, you see the damping go down, and that's at about 28 kilometre scale. So your 4-kilometre grid spacing model is resolving scales of motion greater than about 28 kilometres. The 10-kilometre, it's at about 70 kilometres. So that's the effective resolution of your model, and that's why people get upset about this. They say, I've got my 1-kilometre resolution model. No, you've got a 1-kilometre grid spacing model that is resolving scales of motion greater than about 7 kilometres. And that number, 7, is not a magic number, it's a model-specific number. It depends on your numerical schemes, it depends on the formulation of your code. Here, there's a little bit of a tail, rolls up at the end, and this is related to grid scale noise, essentially. You're only just resolving these scales at 7 delta x. If you write your paper, you do your analysis, and you've got all these really cool features, and it turns out these features are at scales of motion that are 7 times your grid spacing, you should look at those results quite skeptically, right? That's the minimum resolvable scale of your model. Quite often, depending on the model, depending on the scenario, you can actually see a little bit of a lump there at 7 delta x. There's an accumulation of energy at that smallest resolvable scale. And that can be from unresolved processes that are spurious and they've got more energy, or it could be from an accumulation of energy here from an energy cascade. Right? So a good rule of thumb is to properly resolve a phenomenon, the grid spacing needs to be at least 10 times smaller than the scale of the phenomenon you're interested in. So I'll give you an example for a cloud resolving model. And the arguments here are quite similar between the atmosphere and the ocean. We talk about convection permitting modelling and and large eddy permitting modelling, which is quite similar to in the ocean. You have eddy permitting models in the ocean. Yeah.
In your last slide, when like both the curves they were following each other, so they are in like an eddy cascade, which is a larger eddy developing a small eddy.
Yeah.
So does it valid in the inverse energy cascade?
Sorry, the question is there an inverse energy cascade?
Yeah.
That's a good question. So there's a lot of discussion about what causes this mesoscale spectrum, and there's argument whether it's an inverse cascade or non-inverse cascade. I don't know the answer. Craig, what's the answer? Is it an inverse cascade or not?
I don't know. I think before you were talking about that lump that occurs at 7 delta x, you were sort of inferring an inverse cascade from the unresolved scale.
Yeah, that's true.
I imagine this would be going in both directions. But
yeah. I agree. Okay. Okay, so there's a really famous paper by George Bryan who looked at how clouds are resolved by what we used to call cloud resolving models. Go back 15, 20 years, people said, all we need to do is get to 1 kilometre grid spacing in our models and we can resolve clouds and everything's going to be okay. All right? And George wrote this paper where he said, okay, let's test that. And we'll take our model, we'll run it at 1 kilometre grid spacing, we'll run it at smaller and smaller grid spacings down to 125 metres, which was pretty remarkable for 2003 because this is a really expensive calculation. Right, so here's a cross-section through a squall line. I've marked on the cloud there. Here's the cloud and here's the cold pool. And what you see, that we've got this inflow, and this is equivalent potential temperature. Here's our unstable inflow, air coming in, rises above the cold pool, and then you get it's convectively unstable. In your 1 kilometre grid spacing model, this convective instability just manifests itself as this smooth blob of air that rises through the back of the storm, creates a storm that kind of looks like the same storm at higher resolution. But at higher resolution, what you get is that this breaks into these turbulent eddies. And the key thing here, there's a couple of important things. This 1 kilometre model does not resolve the turbulent processes that should be formed by the convective instability. Our eddies in the atmosphere, in these convective clouds, are about 1 kilometre in scale. That's the largest eddy scale, is about 1 kilometre. And at 1 kilometre grid spacing, we're not resolving that. The inflow is about 2 or 3 kilometres across. We're representing that inflow, but we're not properly resolving it. But once you go to 100 metre grid spacing, it starts to resolve those 1 kilometre scale eddies and represent them. And the unstable inflow breaks into these eddies. And around this time, people stopped calling 1 kilometre grid spacing models cloud resolving models because we realised this. And they started to become called as convection permitting models because it was recognised that you need to go to really order 100 metre grid spacing to properly resolve convection. And this is deep convection. If you're thinking about shallow convection, the scales of motion are much smaller again. If you look at a cross-section through here, this is, rather than looking across the line, you look along the line, so you take a cross-section through the middle here. This is what they look like. It's quite different. This is your slab of unstable air that kind of is poorly resolved and just rises through the storm. In your eddy resolving model, a cloud resolving model, this forms into these turbulent plumes. And the spacing of those plumes is about 5 kilometres. So you think, oh, my 1 kilometre grid spacing model should be able to resolve these plumes that are spaced 5 kilometres apart, but they can't because of this implicit numerical damping. That means that the minimum resolvable scale of this model is really 10 kilometres. All right. These errors that come about here. This damping you get here. This comes from two things. To keep all of our models stable, we often add artificial diffusion to just smooth everything out. It's really unpleasant, but we do that. So some of that comes from this artificial imposed diffusion, but some of it comes from implicit diffusion, which comes directly from the numerical scheme, or the truncation errors in the numerical scheme. I'll explain what I mean by that. All right, so this is going back to Numerical Methods 101, which some of you have seen and some of you may not have seen. So what we're doing in all of our models, atmosphere, ocean models, the starting point for the development of every numerical scheme is trying to solve this equation, the one-dimensional advection equation with a fixed value of u, of the velocity. Super simple equation. It's actually quite hard to solve, right? It's quite hard to solve. And you'll see this. We have an analytic solution for this. Here's our analytic solution, right? If you start with an initial condition and you have periodic boundaries and you have a constant velocity, your advection of that solution will just look like this. So this is just the solution to the 1D advection equation with a constant velocity. It blows the signal around. Easy to solve, right? Let's try and make numerical approximations. So use a really good temporal advection scheme. Just make some numerical approximations to that spatial differencing scheme. And here are our different solutions. I've got 4 different spatial differencing schemes here. And as this goes round and around, you see that all of the 4 solutions start to look different and look different from the analytic solution. All right, let's go again. All right, so if you do the simplest form, first order upwind differencing it's called, you get a damped solution. Right, so our analytic solution is one of these curves. I can't work out which one it is. It's one of these curves. Our simplest first order differencing scheme gives us this. Our second order differencing scheme gives us this signal that travels slower and then generates all these waves. Our third order one is damped here. Our fourth order one is really close to the analytic solution, but if you look closely, you'll see it's moving slightly slower.
How many grid points are across the hump?
Oh, heaps. I think there's 100 grid points across here. So there's probably 20 grid points across the hump. Okay, to summarise these examples. And so what I did was I used a really good temporal differencing and different spatial differencing. And this is just the simplest one, the first order differencing. So the leading order error of that spatial differencing scheme controls the solution. And to summarise what we just saw, the first order method is strongly damping, so it's diffusive. The second order method is actually called dispersive, so the signal travels too slowly and separates into component wavelengths, so different scales travel at different speeds. Third order method, damps, is diffusive again. The fourth order method travels too slowly slightly. There's a pattern here, and this is actually a general result, that odd-ordered schemes are diffusive and even-ordered schemes are dispersive. And this comes from the truncation errors. Let me prove this to you. Just with a simple example for the first order differencing. So this is the equation we've used to approximate our solution to the 1D advection equation. And this is equivalent to this, u times d phi dx plus order delta x. So the leading order error term is order delta x. I said remember this, but I'll prove this to you. So you may, for those of you who've done numerical methods courses, you may remember that if you were to take this approximate the first order derivative with this difference equation. It equals to the first order derivative, and this is the leading order error term plus higher order errors of order delta x squared. So this leading order error term is of order delta x, so this is called a first order approximation. But we can use our Taylor series. Here's one that I prepared earlier. And hopefully this looks familiar to you. This is Taylor series. You may have seen it in high school or first year uni, where phi I plus 1 is equal to phi I plus delta x d phi dx plus delta x squared on 2 d2 phi dx squared plus higher order terms. And if you were to write that as, you can write this as phi I minus 1 equals phi I minus delta x times the derivative plus delta x squared, that's a squared, d2 phi dx squared minus, all right. So this is revision. I hope that you've all seen this before. So if I take this second one and I subtract, how do I do it? Oh, I have to multiply it by minus 1 and subtract from both sides. So how do I do this? I'm going to do it minus, minus, plus, minus, plus, minus. So I just multiplied everything by minus 1. And then what I'm going to do is subtract phi I from both sides. So that's minus phi I minus 1 minus phi I gives us plus phi I equals delta x d phi dx minus delta x squared on 2 d2 phi dx squared plus dot dot dot. And then if I divide both sides by delta x, and I'll just do that the easiest way, I'll write delta x under there, wipe that out, wipe that out. What we see is that this equation, which is the difference equation we're using up there, is equal to d phi dx, and the leading order error term is minus delta x on 2 d2 phi dx squared. Plus there's higher order error terms here. Okay, everyone following me? So this is our leading order error term. And what we normally do is we just ignore that. We say our leading order error term is order delta x. But if you retain it, just keep it, we can understand how that leading order error term dominates the solution. All right, so here's our difference equation. Equals d phi dt plus u d phi dx. We'll keep that leading order error term in there, plus order delta x squared. So all we've done is just included that leading order error term. And so retaining that term gives us this equation. That's from the previous slide. We can rearrange that and it looks like this. So now this equation that we're trying to solve, if we keep the leading order error term, we have this extra term in here, which looks a lot like the one-dimensional advection diffusion equation. So while we were trying to solve the 1D advection equation with first order accuracy, what we're actually now doing is solving the 1D advection diffusion equation with second order accuracy. So, while this is a first order approximation to our 1D advection equation, the equation we're trying to solve, it's a second order approximation to the advection diffusion equation. So our difference equation is a better approximation to the advection diffusion equation than it is to the equation we're actually trying to solve. That's the key thing. And you can redo this for a second order scheme and show that the leading order error term is a dispersive term and not a diffusive term, and if you do it for the higher order, the pattern follows. So if we take that equation, that difference equation that we're solving, and we keep all the leading order error terms, just the first one, we get something called the modified equation. And it's the modified equation that's actually determining the form of the solution, not your difference equation that is a lower order approximation to the equation you're trying to solve. So this is the key result here, that these leading order error terms in your numerical schemes actually matter. They really matter, and they really dominate your solution when you're looking at the smallest scales, because they really control the errors at that smallest resolvable scale. So why do we need to know this? So the truncation, what I just said, the truncation errors have a large dominant effect on the solution at the smallest resolvable scale. Whether your scheme is diffusive or dispersive actually really matters. If you think back to this, and say that that variable that we're trying to advect is water vapour mixing ratio, so the concentration of water vapour. Right, we've got a blob of water vapour that we're advecting along. What does negative water vapour mixing ratio mean? Right, so it's important for variables that are one-signed. You don't want them to generate this noise, which you then have to come in and artificially remove that noise and move the water vapour somewhere else. So it does matter. Where were we? Dispersive solutions can be noisy, which can be important for one-signed variables, e.g. water vapour. If you have a dispersive numerical scheme, often you have to put additional damping on top of that to damp out the noise. You need to be careful interpreting any model output at scales less than about 10 delta x, as the spatial temporal variability at these scales is controlled by the numerics, and that's just a fact of life. And so it's useful to know the numerical schemes that your models are using so you know how to interpret the results. All right, I'm going to finish now. My last slide. Summary. Atmospheric models are complicated. So are ocean models. So are all models. They're all complicated. And they've got so many different components. And many of us use them as black boxes, and that's okay. Right? You can do a lot of valuable things by treating models as black boxes. So you don't necessarily need to know the nuances of the code, how the model is parallelized, all those sorts of things. But you should understand their construction, how they're built, the assumptions that are made to build them, and what their limitations are. Because it's really dangerous using a black box that you don't understand its limitations. All aspects of our models are imperfect, but some parts are less perfect than others. And so we should appreciate those. And it really depends on the scales of motion you're considering. And as you get closer and closer to the minimum resolvable scale of your model, it becomes problematic. And that's it. So, and the final slide is, models have all these imperfections, but you can do some amazing things with them. And you can get a level of detail from your models and internally consistent and continuous data sets that is very difficult to achieve from observations alone. Right, so here's a result or a visualization from one of my older large eddy simulations where I've got a cloud and I've got the flow coming out of the back of the cloud and I've got all this analysing the turbulence coming out of the back of the cloud and the flow field coming out of the back of the cloud. Right? And, this is from a model, right? So you need to treat it as a model result, not the real world. But getting this level of detail of all these different variables from observations would be really challenging. So we can do amazing things with our models and learn lots about what the atmosphere is doing using them but we always have to have in the back of our mind that this is a model and it has errors, and we need to understand what those errors are. So that's it. Thank you.
Any final questions at all?
Craig.
Can you go back to that, the first slide you started with, the gazillions of equations and the Reynolds average?
Oh.
So, yeah, any one of those. Yeah. So there you have it down the bottom. You've got this expectation of U prime, W prime. Yeah? And this is meant to represent an average over. So I guess if we go high, you've got U equals U tilde plus U prime. And U tilde, presumably,
it's a resolved
is the scale resolved model. And so what parameterization schemes are trying to get us to say that, for example, that U prime, W prime, average.
Yes.
So would you like to just talk a little bit about, so you've just told us that actually it's 7 delta x.
Yes.
10 delta x, better. But
So,
then if I go to the literature and I look at a parameterization scheme, or I go to the Met Office model, they give me a single column model.
Yeah.
1 delta x across.
yeah,
So this is deeply wrong.
this is deeply wrong, and I guess you missed the discussion we had on the grey zone here,
Right.
where I talked a little bit about this, how the assumptions of our parameterizations break down at some range above our minimum resolvable scale. But the key point I think you're making is that we have this region through here where we're not resolving things properly. We're assuming, and we're trying to parameterize stuff down here. And to calculate our parameterizations, we're actually using the grid scale to calculate our parameterizations. So whereas here's our Richardson number calculation, where we're calculating the Richardson number to define our diffusion coefficient. We're calculating that from the grid scale, whereas we probably should be calculating that from 7 times the grid scale to define those terms. We're not doing that. So we are doing something fundamentally wrong here. So I think that we should either be trying to parameterize everything up to 7 delta x, or that's actually what we should be trying to do. Parameterize everything that's purely unresolved and parameterize the difference between here and here. But we're not doing that. Good question. Zeb?
You talked about model tuning a while ago.
Yeah.
At what point does your tuning take you so far from the physics that starting with the physics was a waste of time?
That's a good question. I wish Gab was here because he would have an answer to this question. You could ask that question at the end of the week when Gab comes and gives his talk. I think there's a lot of over-tuning in models, right? Because there's so many parameters to tune. And I guess I don't have a great answer to this. Hopefully we don't tune the models so much that they go beyond reality. And each of these parameterization schemes, when they're developed, you've got some parameters there, and hopefully if this parameterization is physically based, those parameters have some kind of foundation in observations or theory, and so you've got a little bit of leeway to do the tuning. I guess you could theoretically tune them beyond that leeway. Craig wants to comment.
So Todd had the flux form of the equations down there. It's really nice when you have a flux form because often you can get like a Gauss type theorem constraint about the amount of energy going into a bus and the amount of energy leaving it. So I think, within that constraint of like saying, okay, if I integrate over the entire grid column or something like that, I'm preserving some things I care about, like the amount of H2O, liquid water or ice form, or momentum or energy. So just, I guess, a few physical constraints where we really feel strongly that, physics obeys that. then having those in. But apart from that, yeah, who knows? So. Yeah.
Thanks, Todd.
All right, thank you.